All right, pushing a piano up an incline. Lots of cool physics in this one. For one thing, it's on an incline. So we'll do components again. And the knee-jerk reaction that looks like normal force is on a funny angle. We got to fight that. It's actually components of gravity that we need to find. And the other cool thing that's just specific to this one is I made it up that said it's going at a constant speed. So technically it's not accelerating. When we draw the free body diagram, I'm picturing a long thing going that way. We got a piano on it. And then some poor guy pushing it up the hill. It says it's a 10-degree incline, so that means the 10 degrees fits in down there. Gravity's pulling this thing straight down. Normal force by definition is always perpendicular to the incline, so I'm going to draw it that way, Fn. Friction, since they're pushing it uphill, friction's going to be downhill. And they're pushing it up the hill, so that's our F applied. It doesn't say any different, so I'm going to assume that they're pushing it parallel to the incline. If they weren't, it would become a little bit trickier component-wise, but it doesn't say they're not. And pianos normally you're about as tall as them, so you would push them parallel to the plane they're moving in. Gravity's the one that's on the funny angle. It's accelerating in the plane of the incline, and gravity's not parallel or perpendicular to that. So I need to find this component of gravity. I'm going to call that the perpendicular, and that component of gravity. The 90 fits in between those two. The parallel component is opposite the angle. The perpendicular component is adjacent to the angle. The angle 10 degrees fits in at the top of the triangle. So it kind of looks like that. Then we can use those skills we did before. Instead of vertical, consider the perpendicular. It doesn't say anything about this flying up into the air or falling down through the ramp, so that means the normal force is balancing the perpendicular component of gravity. In this case, well, perpendicular component has been pretty much every time adjacent to the angle. If we keep drawing it the same way, it's going to keep being a cosine. We could crunch that out, but I'm going to leave that for later. In the parallel component, we could set up F net equals ma, but the a is 0. So I'm going to do it a little bit differently. I'm going to say that the uphill forces must be completely balanced by the downhill forces. In this particular one, there's only one uphill force. That's how hard the guy's pushing it, or the person's pushing it. There's two downhill forces, the component of gravity and the component of friction. I think because of the way I drew the triangle where the F parallel is way down at the bottom of the triangle, often when people do this question, they kind of forget about FG parallel. And they tell me that the F applied is just equal to FF. It's not just the FF. You got to beat friction and then some to push this thing up a hill. Friction and the component of gravity have to be overcome. Our perpendicular component of gravity, it's opposite the angle, so that's an mg sine relationship. Friction is always mu times Fn, so in this case it turns into mu, and the Fn was that cosine thing, so mu mg cosine 10 degrees. We could factor out the mg if you wanted. Realistically though, we're going to crank it out on a calculator. I get the first term working out to being 680, and that second friction term being 965. So my F applied, I get 1645. Same skills that we've been using in all our forces questions, just we had to do some funny component work on gravity, since gravity was on a funny angle compared to